Okay, so welcome to this course on Newtonian cosmology. Obviously, the circumstances we find ourselves in mean that we cannot deliver this course in the traditional lecture plus problems class route. And so I'm going to try and provide as much material as I can, and hopefully things which are useful online. And with that end, the notes for this course are going to contain two things. So the first is a set of PDF notes, which will be available via Brightspace. That is essentially fulfilling the role of a textbook, as I'm aware you can't get to the library, and will contain all of the maths and all of the descriptions that you need to know for this course. And then in these videos, what I will do is something a little bit closer to a traditional lecture, where I actually run through some of the sort of core elements. And it won't be quite as discursive perhaps as a lecture, but it will do a similar job. And so if you find that you learn better by copying down a set of notes which are written on the board, then this is the thing to do. And perhaps also I will say a few more explanatory words here that I don't perhaps say in the textbook. So here might be a good place to come if there's something in the textbook that you don't understand. And so, we will kick off with this. My aim in all of this is to try and provide a useful course and to try and make sure that you have all that you need to pass this course at the end, bearing in mind that, obviously this is an unusual situation for everybody. Some of you may have things which mean you can't be available at certain times. You may have caring responsibilities. Unfortunately, some of us at some point may even be ill. And so hopefully all of this is available to you online at the time that works for you. And there's some more details about how the course will work just written on the front page of Brightspace as well. So, to start with just a few words about what cosmology is. You can think of cosmology as the study of the universe on the largest of scales. And that's just a very simple way of looking at it. And by that I mean we're not interested in stars or planets or even individual galaxies. We're interested in the universe as a whole. And in a sense, cosmological questions are questions which have existed for a very long time, because people have always wondered, where did we come from, where are we going? And so if you're interested in, where did the universe begin? Where is the centre of the universe? Questions like this are important, and therefore they've been important for thousands of years. And as a modern science, we're interested in measuring things like the size of the universe, the shape of the universe, and the age of the universe. They're the sort of things we're after. And in this lecture, this first topic, what I'm really going to talk about is a set of fundamental observations which govern our view of the universe today. And so these observations are, in a certain sense, very basic, but in another sense, they have to be things which are explained by any model of the universe that we come up with. And I'm going to start off with this first observation. The night sky is dark. And you might be thinking now, right, my lecture is barely 3 minutes in and he's already talking about the completely obvious. But actually there is some quite profound information contained in the fact that the night sky is dark. And this is actually a well-known statement. It's something called Olbers' paradox. And it's an interesting feature that if you look at the night sky, it is mostly empty. And so even if I look, for example, at some of the most extreme images of the universe that we've seen. So this is the Hubble Ultra Deep Field. It's what you get when you take the Hubble Space Telescope, which is the most sensitive telescope we've ever made, and you point it for several weeks at one spot. And what you see here is mostly galaxies. It's being chosen to be a bit of sky where you don't see a lot of stars. It's mostly galaxies. But what you also notice is that although it's got many thousands of galaxies in it, it is still mostly black. That is, not every single line of sight that you have ends on a star or a galaxy. And you can actually do a little bit with this to make things clearer. And so if we imagine that we're sitting here. And what we have is we have some stars which are distributed through space at some uniform density. That means the number of stars per cubic meter, or if you're doing cosmology terms, per cubic megaparsec, or something like that, is in fact constant. And then you ask yourself some questions. So let's just sort of set this up, and hopefully this will draw in a way that I can then sort of fix. Okay, let me move this across. Let's put this somewhere in the middle. There we go. And then another circle on the outside. So if I imagine that I'm the observer sitting here on the Earth, and I'm looking at all the stars around me, and I have some distance here which is r, and then I'm going to cut these into thin shells which have radius dr, and this is spherical, this is a 3D projection of that. And I'm going to say that the stars are uniformly distributed through space. And that means they have some number density, which is n, and that's got some unit which is, per meter cubed or per megaparsec cubed if you're a cosmologist. And then I have a measured brightness of each star, and that's what we call the flux of each star. And let's just, for the sake of simplicity, assume that all the stars are the same. Actually, it doesn't matter whether that's true or not for what's going to see here, but let's just assume that all the stars are the same. And the measured brightness of the star, that's the flux, so that's the watts per meter squared, if you like. I'll call this F, and that's equal to the luminosity of the star, or its power, divided by 4 pi r squared. In other words, I take my luminosity, I illuminate the surface of the inside surface of a sphere with that star. Now, of course, I don't just have one star, I have very, very many stars. So what I'm going to do, and what I've drawn up here, is essentially splitting this into a series of shells. And then I can look at the number of stars per shell, and that is just the number density, n, times the volume of the shell, which is 4 pi r squared, the surface area of a sphere, times the width of the shell. And now I can start looking at the brightness of each shell. And I'm going to call that Dj, and that's equal to the flux of each star, L over 4 pi r squared, multiplied by the number of stars that are in that volume. And then I can integrate it. And that's relatively simple, because of course most of these things cancel. So again, this cancels, and what I end up with is the integral of NL, they're just constants, the integral between 0 and infinity of dr. And that becomes, surprise, surprise, infinity. So in other words, if I have an infinite, uniformly filled universe, the sky should be blindingly bright. And then you can ask what that means. What's the solution to that problem? Because clearly it is a paradox in the sense that the sky is dark. That means that some assumption here in infinite uniformly filled universe is wrong. And the solution is straightforward, but not quite necessarily the one you would think of. And the most obvious solution, of course, is you say the universe is not infinite. That's the first thing you would come up with. And you're right, but actually the correct statement is that it's not infinite in age. It may or may not be infinite in extent. We don't know that statement at the moment, at least at this point in the course. But the point is that if the universe has a finite age, then light from distant stars travelling at the speed of light has only had time to travel the speed of light times the age of the universe, and therefore we haven't seen it yet. So light from distant stars is not yet seen. And then you can go a little bit further. You can also say there is insufficient energy, or more officially probably mass energy, inside our horizon to make the sky bright. And here by mass energy, I'm talking about just taking all of the energy, even take all the stars and you convert them to energy with E equals mc squared. There is not enough energy to make the sky bright. And by horizon here, I basically mean the speed of light times the age of the universe. And there are a few other things that contribute to why the night sky is dark. So for example, it's also true that light is redshifted, which we'll see in the next video. There are also things that people have thought about that don't contribute. For example, people think about what if there's just lots of dust in space and we stick that between the stars and us? Well, that doesn't work because eventually you have to heat the dust up and then you start to see it, at least in infrared light. And so the solution to the Olbers paradox is in fact quite profound because it immediately tells us that we are dealing with a universe which had a beginning. It has not been here for an infinite amount of time. It is an event which has a beginning. And so our cosmological models must take that into account.